Waves. Let's talk waves. The image here is a sunset right off of this island in the background. We were camping. We camp every Christmas in the Keys. The wind was kind of going from all different directions. So you can see the water had a lot of chop to it, and there's a lot of curvature to the islands there. So the waves are usually not real consistent, uniform sets of waves. It's kind of choppy out there in the water off of the Florida Keys. All right, what are some influences on wave activity in our ocean basins? My laundry. The wind. The wind is what generates waves. This image up above is my two kids in the ocean in a kayak, I think. This is off of the coast of South Carolina near Pawleys Island. So spend a lot of time at the beach. So wind. Wind is going to generate waves. We are also going to talk about tsunamis, and these are generated by displacement of the seafloor. What's going to calm the waves down then? So the waves just don't keep going forever. There's surface tension, and that surface tension is going to calm waves down. And then gravity, right? So the waves are moving, well, gravity is going to act to dampen that wave activity. Capillary waves just mean tiny little waves. The restoring force is the surface tension. So these are little wrinkles in the surface of the water, and they usually don't last very long. It'll be like a gust of wind and a bunch of tiny little waves. And these are going to form as the wind drags across the water. It blows across the water. The wind is going to drag the water as it blows across the water. In that case, then, the energy from the moving atmosphere is transferred down into the water. Those capillary waves give the wind something to grab onto if it keeps blowing. So gust of wind causes a little capillary waves. When the wind keeps blowing, then it's going to make the waves bigger and bigger. What would restore that surface of the ocean back to flat would be gravity. Gravity would bring it back to a flat surface. These are the most common waves. We're going to split the waves into two groups. One is the deep water waves. That's water out in deep water. And we'll talk about what that means in a second. But the other classification is the shallow water waves. And it has to do with wave height and wavelength. So the wave, we see it at the surface, but it actually is moving water at depth as well. And if a deep water wave then doesn't interact with the seafloor, but a shallow water wave is going to interact with the seafloor. So all of this is based on the depth of the water. Deep water waves, they're not going to interact with the seafloor. Shallow water waves, they do. So in the definition here, L is the wavelength. So if the depth of the water is greater than that wavelength divided by 2, it's still a deep water wave. Once the depth of water shallows up and is less than that wavelength divided by 2, that should be a 2, then it is going to be a shallow water wave. Okay, I fixed the typo on the fly. So the depth of the water in a shallow water wave is going to be less than the wavelength divided by 2, not 20. All right, let's look at parts of the wave. So we mentioned wavelength. Let me turn my face off for a sec. The wavelength is the distance from crest to crest. The wave height is the height from the top of the crest to the bottom of the trough. And here's the trough. The crest is the top of the wave. The wave period is the time required for the wave crest at point A to reach point B. So it would be like crest, 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 crest. If that makes any sense, that period of time between each clap would be the wave period. The wave frequency is the number of wave crests passing each point each second. So that just makes the time, a second, and how many crests pass in that time. We can also measure the steepness of a wave. It's kind of a funny geometric calculation here where you take the wavelength and the wave height into account, and then that angle there is the steepness, is the height divided by the length of the wavelength of the wave. There is another term that's called celerity, and it is the wave speed. So another fancy word. Move my face out of my way. I don't think you can see it. But here's that same kid out in the Keys at sunset. The speed of the wave, this celerity value, is the wavelength divided by the wave period. So we just defined on the last slide what those were, so go back and look if you need to see. Once a wave is created, the speed may change, but the period stays the same. Once that's set up for a wave, it stays the same. In deep water, the wave speed is going to depend on the wavelength. In shallow water, remember, we're interacting now with the sea floor, so the actual speed of the wave is going to depend on how deep the water is. All right, this is what I was talking about with how we see the wave at the surface, but it's actually going to be affecting water down to a depth of the wavelength divided by 2. So that defines the zone where particles, molecules of water are going to be moving in these circular orbital patterns. They start out big at the surface. That orbit is the size of basically the wave height, and then it diminishes down till no motion once you get to half of the wavelength. All right, we can calculate speed or celerity here. It's a function of a property, the length or the period of the wave. So here's the equation. So C is that speed equals its gravity is the little g times L, the wavelength, divided by 2 times pi. Well, we know gravity, and we know 2, and we know pi, so we can reduce that equation to 1.25 times the square root of the wavelength. Okay, so that is how we're going to determine the speed in deep water, just looking at the wavelength. Progressive wind waves from storms. So storms are usually going to have a storm center to them out at sea, and the waves that are produced by storms are going to have different wavelengths and different periods. They're going to propagate away from that storm, like move away from that storm center in all directions. That's called a swell, the storm swell. And how much that disperses over time and changes over time is going to depend on that beginning wavelength and period. So here we have in the beginning an area of wave generation around that storm center. It doesn't necessarily have to be a hurricane, but it could be these rotating storms. In the beginning, there's going to be these combined long, intermediate, and short wave periods. Eventually, those are going to get dampened out till we have long and intermediate wave periods, and then away from that storm is going to be long period waves. And this term here, swell, are those long period waves that come off of a storm center. There are also waves that can interfere with each other. So I remember doing this in like a physics class in high school, where you would create waves and then create waves in another direction. And those waves can add and subtract each other. So if 2 waves are coming at each other and they're in phase, they can add. So here we have in the image wave 1 coming in and wave 2 from another direction, but the crests meet at a high point, at the crest meet at the same point, they're going to add together. And so that wave essentially doubles. Whereas if you take waves from one direction and another direction and they're out of phase, they essentially cancel each other out. So you can make bigger waves if they add up, or you can cancel out or dampen waves if they have this destructive interference where they're out of phase. Wave height, so the size of a wave is determined by three essential factors here: the speed of the wind, and then the duration, or how long has the wind blowing, and then this last one might be a new term for you. It's fetch, and that's the open water distance across which the wind blows. So if all three of those together are working together, and you have a high speed, a long enough duration, and a big enough fetch, that's when you get really big waves. This image shows wave heights in the ocean. It's from your book. The Southern Sea there, the Southern Hemisphere, has the biggest waves. There are waves in the sea called rogue waves, and they are unusually high. I recently read a book about rogue waves. I highly recommend it. It's about the science of rogue waves, but it's also about the history of rogue waves, and then also about surfing. If you know anything about the surfing world, it's always this macho thing, and even some women are getting into it, like who can surf the biggest wave. They take jet skis out to be safe, to get them to and from the wave. So the book I read is about rogue waves, is really good about that whole culture. So these are abnormally high waves, and if you're out at sea in a ship, it can be really dangerous. And they usually are going to occur because of that phenomenon we looked at a couple slides ago, this constructive wave interference, where there's two waves that have come together and they add to each other, and they are going to make a very big wave. They also are associated with coastlines where there's a big change in depth. So we'll see surfers coming to beaches where there's a big drop off, and then the waves get set up off that drop off. They're really big when there's that change in depth. And then there's usually a factor of the currents, those horizontal movements of water out at sea. So coming together to make rogue waves. All right, well, let's move. Turn my face back on. Hi. Shallow water waves. So now we're coming into the beach. There's my kid again, and I believe that's my sister on the left and my niece in the middle. This would be back at Pawleys Island. We go there because my parents live there. Okay, that says shallow water waves. So these, instead of wavelength being the main factor is going to be depth. So in the equation here, we're not using wavelength anymore, we're using the depth. Okay, square root of depth. All right, here are those waves coming into the shoreline. So deep water waves, we just went over, they're out here. This is where the depth is greater than half of the, greater than the wavelength divided by 2. The speed and the wavelength are constant and depend on the wave period, and period is, the height is constant, just coming into the shore. Okay. When the wave starts to feel the bottom is at half the wavelength, and here we have these intermediate waves. The speed and the wavelength are going to decrease, so the actual wave is going to compress, and in that volume of water is going to need to stay the same, so the wave actually gets higher. So see here, out at sea we have this long wavelength, intermediate waves, shorter wavelength, and the wave gets higher. There's a point where then that wave is going to tip over, and those are breaking waves. So now we're coming into the shoreline, and the height is going to increase until it topples over. All right, here's that depth is less than the length divided by 20. Remember, I corrected it on the other slide. I changed it on the other slide because I had forgotten to recall that we had those intermediate waves. So really the shallow water waves, I was mistaken, are going to be that wavelength divided by 20. So this is beyond where, so that the waves, I wasn't totally wrong. The waves are going to feel the bottom at wavelength divided by 2, but be classified as shallow water waves where the motion kind of changes. You can see the orbitals here kind of flatten out and become more like an ellipse. So there's a complete change in the way the water moves once you get to the wavelength divided by 20. All right, when the waves come, let me move my face out of the way. Put over here, I like it over there. All right, so waves are coming into the shoreline, they're filling the sea floor. And the seafloor topography is not always going to be uniform. And so parts of the wave may interact with the seafloor before or after other parts of the wave. And so a part of the wave may slow down before another part of the wave. So that's going to make the waves bend as they move into the shoreline. So here is 3 examples of how that works. In the first example, the waves are coming into the shoreline at an angle, which is pretty common. The trace of that yellow line is the wind direction. So wave movement is going to be in the direction of the wind. So if the wind is blowing at an angle to the shoreline, then the waves are going to be coming in at an angle to the shoreline. And the waves in the part of the wave in the top of that image is in shallower water than the wave at the bottom of the image. So what I'm saying is these waves up here, even though they're following the same crest here, this part of the wave is in shallow water compared to this part of the wave. So that wave at the top of the block diagram is this part of it is slowing down with respect to this part of the wave. So that's creating a bend in the wave because now it's moving at different velocities. And it's compressing that wavelength as well. So up here the wave crests are closer together because the wavelength has been compressed, but maybe the wave height is higher. Okay. That did not do anything. I'm wearing them anyway. They're dirty. So here is, that's just waves coming in at an angle because of the way the wind blowing. This next image is showing that the coastline has some topography. So elevated headland just means there's like a promontory, maybe a cliff, and then there are these bays on the side of the elevated headland. That elevated headland is going to extend out to sea. So these dashed lines reflect the bathymetry, the depth of the seafloor. So out here, it's like a ridge coming off of the land. So the wave is going to bend around that elevated headland. And it actually, if you look at the way the wave rays are coming into the elevated headland, it's going to concentrate that wave energy. These yellow lines are called orthogonals. They're drawn perpendicular to the wave crest. They're called wave rays or orthogonals. And those are going to concentrate energy onto the elevated headland, creating more and more erosion at that point. Whereas over here, we'll go to the next image, in these bays, the energy is dispersed. The wave ray is coming in and the wave rays here to the side. That energy is whoop, going to the side. So there's less energy in that bay, which allows for sedimentation. So that would be a place where there would be like a protected beach with not a lot of wave energy. And the energy is on those headlands. All right, this is kind of showing that. Here's wave energy, waves bouncing off these rocks at that headland on the side. And then here on the inside is a quiet bay with some nice waves coming in and leaving that sand in place. All right, here are, so that was wave refraction. Here's a wave reflection. So these waves are coming into this headland, into this cliff. Here are the waves coming in. They hit the cliff and then they're going to bounce back off of that. That actually tends to magnify the wave energy. So you've got a lot of energy coming in and a lot of energy going out. Whereas if you had a beach, that first wave, an A, would just kind of roll up onto the beach, dissipate the energy. Here we're got the energy coming in and that same energy is coming back out. So there are, if you create a barrier at the beach, so this is a natural barrier that the wave is hitting up against and magnifying the energy. If you were to build a wall on a beach, imagine if the wall weren't there, the wave just goes up the beach. But if you put in a seawall, say like in New Jersey, and your waves are pounding against that seawall, they're going to have all that energy kind of reflecting back off of that wall. Okay. So people like to change wave energy because we either have, in this case, like a recreational beach and they're dampening the wave energy. Oftentimes breakwaters like these out in off the shoreline are put in because of maybe there's a marina or moored boats. Moored boats are just like a buoy that's anchored to the seafloor and the boat's just attached to that buoy. And so that wave energy can, make your boat jostle and smash into things, whatever. So these breakwaters look like they're just at a recreational beach to maybe preserve the beach and dissipate some energy. But look at what it's done to the shoreline shape. The waves are coming in through what's basically like a little inlet, and their waves are bending around to the inside of that breakwater. So here's the ocean is out here in the deep water, and it's coming in, and that ray is bending around the breakwater. So what it's doing is making it so there's more energy coming in some points and some not. So there's weird deposition along the shoreline when you have a breakwater like that, changing the wave energy. Okay. The surf zone. So we've went to the deep water, we had intermediate, now we're in shallow water, and now the waves are going to break. There are different kinds of breakers. So breakers, the water particle orbital speed slows in the wave trough more than the crest. So the trough slows down, the crest just breaks over the top of it. There are different kinds. There's plungers where you've got the wave crusting over and you lose more energy more quickly, and these are forming on narrow, steep beach slopes. Spillers are more common where you just kind of have the wave just kind of roll in and gets, foamy at the top versus a nice pretty spillover. And these are forming in wide, flat beach slopes. So when next time you're at the beach, see if you can kind of pick out like, oh, that's a plunger and that's a spiller. All right, here's waves coming into the shoreline. That's definitely a plunger, and these are more spillers rolling in. All right, rip currents are a special kind of current that occurs on coastlines when, in the surf zone, when water gets pushed into the shoreline. You have a mass of water kind of at the beach, builds up, and then it needs to get off of the beach and will just kind of pour out in one main big current. So that water that accumulates in the surf zone needs to get back to sea. And it will do it in kind of a quick, sometimes scary way. So if you're at the beach and you start getting pulled out to sea by the ocean, that's a rip current. Maybe you have a mom like mine that talks about rip currents every time you go into the ocean, and she will tell you it's narrow, that water going back out to sea. So instead of trying to fight it and then getting exhausted and dying, you swim parallel to the beach and you'll get out of the rip current. See this image here? These are rip currents. There's a main one here, but if you just go, 10 feet either way, you should be able to get out of the rip current. These usually occur when there's a swell, right? So those dissipated long wave length waves coming off of a storm. Got a pile water, or the wind is blowing on shore, piles water at the beach, and then it's got to get back out from the beach.